What is something that is in everything?
Something common between
Leaves,
clouds, you, and me. Yes, my friends. Something that is common between everything.
Atoms, you might say. Everything's made of atoms.
But then, there are different types of atoms, aren't there?
The computer chips in my phone are made out of silicon, whereas this wood contains carbon compounds.
But if you look inside the nuclei, or the cores of these atoms,
Deep.
deep enough, then you will find the same beautiful things. And studying these same beautiful things, or the elementary particles of our universe, will lead you to understanding the science
Of everything. The Science of Everything is a new tutorial series I'm starting, which is based around the sciences of particle physics and quantum physics. Personally, I like these two sciences very much, so I'm very excited about this. This video will be tutorial 1, in which we'll be exploring the standard model of particle physics. So, without further ado, let's get straight into it. In a nutshell, the standard model of particle physics is truly the best model or method we have of demonstrating all the elementary particles in our universe. It's like a periodic table of particle physics. Instead of the elements, we have all the different types of elementary particles arranged in a tabular format. This is what the standard model looks like. It contains two classes of particles, which I'll talk about in detail later on. But in this video, we'll be talking about the fermions, or the matter-making particles.
Keep this diagram of the fermions in your mind, because this is essentially what we're going to be using throughout this entire tutorial. Fermions happen to be named after Enrico Fermi, an extraordinary Italian physicist. Fermions are the particles which make up all matter, or stuff, or essentially all the things that you see around you.
Before exploring fermions, let's just quickly first revisit the structure of an atom to just brush up our memories. Inside of an atom, we would find the nucleons grouped together in a nucleus. The nucleons come in two categories, the positively charged protons and the neutrally charged neutrons. Around the nucleus, we would find some electrons orbiting the nucleus in orbital paths called shells.
But our journey just doesn't end there, does it? We still have the neutrons and protons to look inside. Yes, my friends. Just like there are subatomic particles inside atoms, there are, well, elementary particles inside neutrons and protons as well. Protons and neutrons consist of elementary particles, or fermions, called quarks. The neutron consists of one up quark and two down quarks, whereas a proton consists of two ups and one down. Now, you might be wondering what on earth all this up-down business is, but the point I was trying to convey to you was that inside atoms, we find subatomic particles like neutrons, protons, and electrons, and inside these subatomic particles, we find elementary particles called fermions. And at this point, this is where our study of fermions begins.
Referring to our pretty diagram here, we should learn that there are two different types of fermions. First of all, we have the quarks, and then we have the leptons. Now there are many differences between quarks and leptons. Firstly, quarks have fractional charges, while leptons have whole number charges. This means that relative to the charge of an electron, quarks have a portional charge, whereas leptons have whole ones. Also, quarks tend to be heavier than leptons, and they interact with a strong force, while leptons don't. We'll learn about the strong force later on in another video. It's basically one of the fundamental forces of nature. But, as I said, that's for another video. And remember that fermions can't be broken down into anything like atoms can. They're elementary particles, which means they're indivisible. Let's refer to a half chopped up version of our diagram here. From this we can see that there are different ways to arrange quarks. There are many things about quarks. First of all, they come in 6 different types: up, charm, top, down, strange, and bottom. They can be arranged in 2 rows, up type or down type. The up, charm, and top quarks are up type quarks, and the down, strange, and bottom quarks are down type quarks. And they can also be arranged in 3 different generations. The first generation consists of the up and the down quark, the second generation, the charm and the strange quark, and the third generation, the top and the bottom quark. Now, we know that quarks have a particular type of arrangement. That is, they're arranged in 3 different generations. Now, this is not a pointless arrangement, there is a reason behind it, and that is that they're arranged in order of increasing mass. The second generation is heavier than the first one, and the third generation is heavier than the first and the second generations, and is the heaviest out of all of them. We also know that quarks are arranged in up-type and down-type as well. There are up-type quarks and there are down-type quarks. Now there's a reason behind this arrangement as well. Up-type quarks and down-type quarks can change types between each other via the weak nuclear force. An up-type quark can change into a down-type quark and vice versa through the weak nuclear force. And we'll learn what exactly the weak force is in another upcoming video. Now we ought to know that up-type quarks have a charge of positive 2/3 and down-type quarks have a charge of negative 1/3. Now do remember that all these charges that we're talking about are relative to the charge of an electron. Quarks also have the ability to form different types of groups. Any 3 types of quarks grouped together form a baryon, and any 1 antiquark and quark paired together form a meson. Neutrons are the most popular example of baryons, and kaons are the most popular examples of mesons. We'll learn about what exactly antiquarks are in another upcoming video. If you're really desperate to learn about what they are, then you can go watch my film called The Yin and Yang of the Universe, which explains everything you need to know about antimatter. But for now, let's stick to this video. Now that we've got our brains jam-packed with information about quarks, let's dive into the leptons, which are the other category of the fermions, the matter-making particles. We've learned some properties about the quarks, and it won't hurt to learn some properties of the leptons as well. Many of these properties hold true for quarks as well, such as the first property listed here. Leptons come in 6 different types, as do the quarks. They're arranged in 2 different rows. The first row consists of the charged leptons, and the second row consists of the neutrinos. They're arranged in 3 different generations, and unlike quarks, this is important, leptons cannot be influenced by the strong force. And the electron is the most common type of lepton because it's found in atoms, and atoms, as you must know, make up most of matter. Now you might be wondering why charged leptons are called charged leptons and why neutrinos are called neutrinos. It's quite self-explanatory. Charged leptons have a charge of positive 2/3, and remember again, this is all relative to the charge of an electron, and neutrinos have a charge of 0. They're neutral, they don't have a charge. Now we've done this for quarks, and it won't hurt doing it again for leptons. We'll just do it for the fun of it. Leptons come in 3 different generations, as I told you, and the purpose of this is to categorize them in increasing order of mass. Every generation is heavier than the previous generation. Leptons have a special property which allows them to transform between each other. A lepton, a charged lepton, can transform into a neutrino and vice versa. via the weak nuclear force. Now there's another special property of leptons, specifically the neutrinos, which we should look into. It's called Neutrino Oscillation, in which basically neutrinos can change types between each other. An electron neutrino can become a muon neutrino and a tau neutrino, and vice versa, with a muon neutrino becoming a tau neutrino, and as I said, vice versa. Now let's study the gauge.
Whoa, hold your horses. Jumping a bit far ahead, aren't you? Gauge bosons are for the next tutorial. I have to say, making this tutorial took a lot of time, so I hope you appreciated it and learned something from it or enjoyed it. I hope I've sparked your interest in particle physics, or just physics in general, because if I haven't, then I haven't done my job. I've failed. Stay tuned for more interesting videos. Stay tuned for the second tutorial. Not just the second tutorial, but other videos as well, like black hole bombs and weird wildlife. And a surprise video before 2019 ends. So stay tuned, and I'll see you later.